Hi Bobcats! In this video we're going to take a look at a little bit of a shortcut in the method of initial rates. If what I do here works for you, by all means feel free to use it, and if it doesn't work for you, go back to what we were doing in the previous videos. Writing the whole thing out the whole way will always get you the right answer. In this example, the reaction is A plus B yields C, and we have 3 experimental runs. If we compare experiment 1 and experiment 2, you'll notice that A remains constant, but B has been multiplied by 4, right? We've gone from 0.1 to 0.4, and then the rate accordingly changes. So let's look at those two experiments, and what I'm looking for is to take the ratio of the rates and set that equal to the concentration ratios raised to the order that goes with reagent B, which I'll call that N. So I guess I should have written this out. I'm working on the assumption that the rate is given by K times the concentration of A raised to the M power times the concentration of B raised to the nth power. Since A is the one being held constant, it just simply cancels out, and B, the ratio of the concentrations of B, that's the ratio that we're interested in. Again, we want to take the bigger numbers over the smaller numbers, so for the rates, we're going to take the rate from experiment 2 over the rate from experiment 1, so that'll be 0.016 divided by 0.001, and that will be equal to the concentration ratio. So we're going to have 0.4 from experiment 2 divided by 0.1 from experiment 1, and that's all going to be raised to the nth power. Let's see, over on the left-hand side, if we take 0.016 divided by 0.001, that will give us 16. And then the concentration ratio of 0.4 over 0.1 is 4. And that's all raised to the nth power. So the exponent that we need here to make this a true statement is 2, because if 4 is squared, we get 16. And so that means that this reaction is second order in B. All right, so we know that N is equal to 2. Now on the next slide, we're going to go after M and a numerical value for K. To start off our search for M, remember that we're working with rate is equal to K times A to the M times the concentration of B squared. So we already know the exponent on B, we're looking for the exponent on A, so we're looking to compare two experiments where B is held constant. B is held constant between experiments 2 and 3, and it looks like the ratio here is 3 on the concentrations, and then on the rates, we have a ratio of 0.144 divided by 0.0116. So in going after the exponent on A, we're going to have the ratio of the rates, which will be, let's see, experiment 3 over experiment 2, so we'll have 0.144 divided by 0.016 is equal to, now the concentration ratio would be 0.30 divided by 0.10, and that's all raised to the M power. Now if I take 0.144 and divide that by 0.016, I get a value of 9. I have 9 on the left-hand side, and then 0.3 divided by 0.1 is 3 to the M power, and so that's going to tell us that M is 2. So this reaction is also second order with respect to A. So that means second order with respect to A. All right, so our rate law is K times A squared times B squared. And to get a numerical value for K, I can take this equation that we just wrote and divide both sides of the equation by A squared, B squared. That'll give us K all by itself. And rewriting that so that K is on the left-hand side, we have the rate is equal to K divided by A squared times B squared. To get a number for K, I can plug in any one of these three experiments. Looking at the numbers, experiment number 1 has the easiest numbers to work with, so that's the one I'll go with. The rate is 0.001. A squared will be 0.1 squared. B squared will be 0.1 squared. And if I run that through my calculator, let's see, 0.001 divided by 0.1 squared, and also divided by 0.1 squared, that gives me a value of 10. And let's see, in terms of units, the rate has units of molarity per second, and A has units of molarity squared, and for B we end up with molarity squared as well. So one of the molarities in the bottom cancels out with the molarity in the top, giving us inverse seconds divided by molarity to the third power, which gives us molarity to the -3 and seconds to the -1. So the strategy that I took this time around was to look for 2 experiments where the concentration of one reagent was held constant and the other one changed. Took the ratio of the concentrations and raised that to the order and set that equal to the ratio of the rates. This is the exact same process that we did before. I'm just shortcutting, canceling out K in the top and K in the bottom, and canceling out the concentration that was held constant. If you'd rather write it all out, by all means, it all works out either way, whatever's more comfortable for you. Our objective over this video and the last couple was to use the method of initial rates to use experimental data to determine the rate laws for some chemical reactions.